Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Inshallah, now we will continue talking about sampling. Last time we went through the first sampling method, which is prior sampling, and we said that it is good to estimate the joint distribution. Okay, and towards the end of the lecture, we talked about the drawback of this method, which was that sometimes we have an evidence that is very rare, so we might not have it in the samples that we draw. So something like this probability cannot be estimated given these samples, simply because that evidence minus R and minus W didn't appear at all in the samples. Okay, so that's a drawback for prior sampling. So this will be fixed by rejection sampling. So in rejection sampling, let's say that we want to compute this probability P of C given plus S given this network. What we will do is that we will only count the outcomes of C, but ignore or reject samples that don't have the evidence. So the evidence here is plus S. So any sample that doesn't have S equals plus S, which means that it is not matching the evidence, will be completely rejected. So for example, if I got this sample, I will start by getting plus C, then minus S. I should not continue, and I will just ignore the entire sample. Why? Why did we reject it? Because it doesn't match, or it's not consistent with the evidence that we have. So the evidence that we have is plus S. That's what we want to get in the probability that we want. And it's not consistent with the sample, so we will reject it. The next one, we got plus S, so we should continue the sample and we count it. This one also is plus S, so we count it. This one is minus S, so we should ignore it. And we should even stop here and don't sample from R and W, because the sample anyway will not be considered. And same for the last one. So out of these 5 samples, we only get 2 of them. This one and this one that were not rejected. This is called rejection sampling, because we reject or we stop any sample that is not consistent with the evidence. Okay? Now, if we compute the sampling probability, of course, for the samples that survived, they will be consistent with the joint probability, because we just sampled the whole sample, the whole set of variables. Okay, so it is exactly like consistency in prior sampling, which means that it will be correct in the limit. If we draw infinite number of samples, the probabilities, the estimated probabilities that we will get will be very close to the actual joint probability. So here is the algorithm of sampling one sample using rejection sampling. You will see that it is exactly like prior sampling, except in 2 positions. The first one is that we have an evidence. In prior sampling, we didn't have any evidence. Okay, so that's why it's good for estimating joint probabilities. Here we have evidence. So that's the first difference. The second difference, which is of course more important, is that when we sample from a specific variable, if that sample is not consistent with the evidence, we just reject it, which means that we will not return any sample from that procedure. Remember that this is an algorithm to get one sample. So whenever we sample from a variable and the value that we got from that variable is not the observed evidence that we want, we'll just reject this sample. Okay? Any question about how it works? I think it's really straightforward. Any questions? Okay. Type. What is the problem with that? What could be a problem with rejection sampling? Any idea? What could be the problem with rejection sampling? Faisal? What do you mean by You mean you cannot get other probabilities other than the condition with the evidence? Okay, but assuming that this is what you really need, that's not a problem. But yes, in general, we cannot compute any probability that we want. Okay, so that's one. What else? What is more severe than that? Is it wasting any of our time, this method? And we know that we want to get samples that have this observed values. Yes, Faisal again. So say it again, Faisal. So what is the problem? Don't solve the problem before you telling me what the problem is. Okay. So you want to sample first from the observed variables, from the evidence variables. But we cannot sample from the observed variables unless we sample from their parents. That's how sampling will work, right? We cannot, because we don't know the distribution of these variables first. So that's not exactly the problem. And Mustafa, I think, said that underfitting and overfitting. I think you are affected by machine learning session. There's nothing here about overfitting or underfitting. So the problem here is that we waste a lot of time getting samples that we will eventually ignore, we will reject. Yani in the previous example, you saw here 5 samples, we ignored 3 of them. So more than 50% of the samples, after we sample them, we ignore them. Okay, so that's a waste of time, of course, and it will be more severe if the evidence is really rare. Okay, so we might wait maybe 100 samples or 200 samples before we get that event. So that's an advantage. That's the first advantage. The second one, the first disadvantage, of course, or first problem. The second one is that when we do the sampling, we didn't exploit the fact that we know the evidence at all. Okay, we did the sampling only when we get an inconsistent sample, but other than that, we don't exploit the knowledge that we have about the evidence. So, for example, here, this is a very simple network of getting colored shapes. Okay, so let's say that we have just 2 nodes, shape and color, and let's say that I want to compute the probability of a shape given that the color is blue. So the evidence here is that the shape will be blue. Okay, so I get samples and I will reject them, most of them or many of them. So pyramid green will be rejected because we want blue. Pyramid red, rejected. Sphere blue, we will keep it because it has blue. Cube red will be rejected. Sphere green will be rejected. So we didn't use the fact that we want blue at all when we do the sampling. Okay, and as you see here, we wasted a lot of time in rejecting the samples that are not consistent with the evidence. So the solution to that is one solution to that is the method called likelihood weighting sampling. So in likelihood weighting sampling, we say, okay, we want this evidence. Why don't we avoid sampling from these variables and just fix the values of them to the observed value? So we don't need to sample from them. We just assume that we got that value from the sample. In that case, the shapes will always be blue. So we'll fix evidence variables and sample the rest. And all the non-observed variables, non-evidence variables, we will sample them. But for the evidence variables, we will not sample. Why we need to sample them if we are just waiting for the values to be the values that we observed? We'll just fix them to the observed values. So in the previous example, we just fix the color to be blue. So we will not sample from that variable. We'll just sample from the shape. So all samples will be consistent with the evidence in this case. So we'll get pyramid, and then we'll assume that we got blue. So pyramid blue, sphere blue, cube blue, sphere blue, and so on. All the samples will be blue. So we will not waste anything. Okay? So this is called likelihood weighting, and we will know why it is called likelihood weighting. But at least we fixed the problem of the time wasted in rejection. We will not reject any sample now, because we will not actually sample from the observed variables. Why should we sample from the observed variables if we already want their samples to be a specific value? So we'll just fix it to that value. We don't sample from them, and we sample from the others. So that's the idea, the main idea of likelihood weighting. Okay? Any question about that? Yes, Faisal. Yes. Great. Yeah, great. That's great. Yes. Yes. So that's now the problem that we will fix. Okay? But in terms of time, we don't have any waste of time, right? But as you said, the distribution that we will get is not the actual distribution, because we didn't sample from the observed variable. So to fix that, we will have to give a weight to every sample. So the problem here, as Faisal indicated nicely, the sample distribution is not consistent. Actually, if we sample from that, we will not eventually, by infinite samples, will get close to the actual joint probabilities. Okay, so we need to fix that. We'll fix that by giving a probability of the evidence, by adding back, by augmenting back the probability that we didn't actually sample by. So remember, we had evidence variables, so we didn't sample from them at all, and non-evidence variables, we sampled from them. So what is missing here is the probability of getting the observed value, and that's what will be the weight of the sample. That's why it's called likelihood weighting. Every sample will have a weight. So far, the weight of the samples were 1. When we count the number of when we estimate a probability, we count the samples, right? That's assuming that the weight of each sample is 1. But here in this method, the weight will no longer be 1 for some of the samples. So we'll have to assign a weight, and that weight will make the distribution that we'll get to be consistent, to be with infinite samples, we'll get close to the exact probabilities. So let's see an example of how we do this weighting, and then get back to the fact that now we have a consistent sampling. Let's get back to the example we saw last time: cloudy, sprinkler, rain, and wet grass. And let's do likelihood weighting here, assuming that we want to fix sprinkler to plus S and fix wet grass to plus W, because we have greens here. Okay, so that's the evidence now. So remember, in likelihood weighting, we do sampling only for the non-evidence variables. Where are the non-evidence variables? Cloudy and rain. So we'll start with cloudy. The distribution of cloudy is this one, is the prior distribution. So we'll get a sample from that. Let's say that we got green, which means plus C. So we got plus C from here. Okay, so we'll continue the order of the variables as before. So next we'll get to sprinkler. Now sprinkler is observed variable. So we will not sample from that, because we know that we want the value to be plus S. We will not sample, but we will multiply by the missing probability. So we'll assume that initially the weight of that sample is 1, and then for every observed variable, we will multiply by the probability that was not used for sampling for that variable. What is that probability? It's the probability of the observed value, which is plus S, given its parent. What is its parent here? Cloudy, which was plus C. Type. Where is that probability? Do we have this probability? Of course we have it in the conditional probability table. Plus C plus S. Plus S plus C. So this probability is actually 0.1. So we will erase it and put multiplied by 0.1. Okay, so that's so far the weight of the sample. We didn't finish yet. Okay, the weight will be finished by going through all variables. We didn't get through all variables yet. Okay, so that's sprinkler. Now we switch to rain. Okay, so we switch to rain. Now rain, which distribution for rain we will sample from? Rain is non-observed, right? So we'll have to sample from it. Which distribution? It depends on the value of the parent. So plus C, so we'll get a sample from that distribution. Let's say that we got it again green, which means plus R. So we got plus R from here. Okay. For the non-observed variable, we will not change the weight because we sampled from it. The weight here is just for the fact that we didn't sample. We will augment that weight with the sample because we didn't sample from some variables. So that's why we need to fix its probability. We need to fix its probability. Okay. So the last one is wet grass. Now wet grass is observed. So we'll not sample from it, but we will need to update the weight of the sample. So how will we update the weight of the sample? Now we need the probability of plus W given the parents, right? Given the observed value of given the values of the parents, plus S and plus R, plus S and plus R. So the what is that value? This is plus S plus R plus W, which is this value. So this will be 0.99. Are we done? Yes, we are done because that was the last variable, and that will be the weight of this sample. So we got that sample now. Okay, plus C plus S plus R plus W, and its weight is whatever the value will be, which I think will be 0.099. Okay. Any question about how we did the calculations here? And notice in the previous slide, in the algorithm slide, where is it? Oh, we didn't get to the algorithm yet. Yeah, that's next time. Any question? Next slide. Any question about the computations here? Any questions? Okay, so here's the algorithm. Notice here that the initial weight is 1 for every sample. Again, this is the algorithm for drawing one sample. So the initial weight is 1. And now we have two types of variables. If the variable is evidence variable, then we will update the weight by the probability of the observed value given the parents. Else, which is non-evidence, in that case, we will just sample from its distribution. Notice that eventually we will return the sample along with its weight. Now, when we calculate any probability, instead of just adding 1 for that sample, we will add W. And instead of sometimes we divide by the number of samples, right? We will not divide by the number of samples, we will divide by the sum of the weights of the samples. Okay, which is normalizing the values. So that's the difference. That's the major difference between prior sampling and rejection sampling from one side and likelihood weighting sampling. Likelihood weighting, we have a weight for every sample. In the other two methods, we also have a weight, by the way, but it's 1. It's just the default weight, which is 1. Every sample is the probability of, the weight of it is 1 because the sampling probability of it is coming from the joint distribution. Okay, but here because we didn't do the sampling for the observed variables, we have to augment it with the weight. Any questions about the algorithm? Is it clear? Okay, type. Now, this is just a note about consistency. the sampling probability of the weighted of the likelihood weighted sampling is just the probability from the non-observed variable, because these are the variables that we sample from. So this is the non-evidence variables. Okay, so that's the sampling probability. But we have also the samples have weights, which is the multiplication of the probabilities of the evidence variables. So these are now the evidence variables. If we multiply both, so this part is the sampling and this part is the weight. When we multiply both, this probability now is consistent with, if we draw infinite samples, will be consistent with the exact joint probability. Because if you remember from BaseNet, the joint probability is the multiplication of all of these. So it's actually a multiplication over all variables of P of, if this is I, P of xi given its parents, which is this multiplication. Okay, but here the sampling was just on the non-evidence, and that's why we have a weight here for the sample. Okay, last time the weight, or in the other two methods, the weight was 1 because the sampling probability was already the joint probability. But here, because we missed the factors for the evidence variable, we'll have to have a weight for the sample when we count it in our estimated probabilities. Okay, and that will make this distribution now consistent and fix the problem that Faisal indicated first, and we discussed in this method. Okay, right, and that's now of course the joint probability. Now, what is good about likelihood weighting is that we don't waste time in rejecting samples, in samples that we don't need eventually. And also, one thing that is good is that if these variables are observed, then when we sample from downstream variables like W, the samples here will be affected by what we observed already. So that's good, okay, because we don't just sample completely random, no, but we sample based on the observed values that we saw. But on the other hand, that's not the case for all variables, because a variable like C, which is upstream from the observed, from the evidence variables, will not, the sampling from that variable will not be affected or influenced at all by the observed, by the evidence. Because if you remember, we go top down. So C, we sample C without knowing anything about S and R. We sample W knowing S and R, but we sample C without knowing anything about the evidence here. So that's a problem, because we want, given that we have that evidence, we want to sample really we want to sample from each variable knowing that we have that evidence. And that will be, inshallah, fixed by the method that we call Gibbs sampling. Unfortunately, we will not have time in this semester or this course to cover Gibbs sampling, but I hope that you will be excited to know how we fix this problem, and you continue exploring this method, because this method is really wide used in BaseNet and in other actually applications. You will hear about Gibbs sampling a lot. Okay, but unfortunately we don't have time to cover it. But now you know at least that the disadvantages of the previous methods, and you know that Gibbs sampling is a solution to them. Any questions about likelihood weighting? So we covered 3 methods of sampling. Prior sampling, which is good for estimating joint probabilities. Rejection sampling, which is good for estimating conditional probabilities, but we will waste a lot of time because we don't fix the evidence variables. When we fix the evidence variables, we get to the likelihood weighting. The problem with that is that now we will not have consistent sampling. To fix that, we will have a weight for each sample. Now, if I have samples, I have to associate every sample with a weight type. Why is that important? Because now if I compute any probability, let's say that we have the evidence. Of course, the evidence will be everywhere, but let's say that I want to compute the probability of plus z given the evidence. Okay, and we have minus z here, plus z here, and minus d here. Okay. Previously, we say this is 2 over 5, right? Because we have 2 samples of plus z over 5. But that's using maybe the other 2 methods. But now, because we are using weighted sampling and we fixed the evidence, now we need to sum the weights of these 2 samples and divide by the sum of all weights in order to get probability of plus z given E. So it's not just counting now, it's weighted counting. Okay, so every sample now, instead of counting it by 1, we count it by its weight. Okay, any questions? Is everything clear? Okay, if you don't have any questions, then we are done with this session and we are done with the material that we have for this course, inshallah. So next time, I will be open to your questions on Tuesday. If you have any questions, I will also try to prepare a couple of questions for revision to you before inshallah, the final exam I think in 2 weeks from today, something like that. I don't remember exactly, but it is something like that, inshallah. As I said, on Thursday, the lecture will be cancelled because of the senior project presentation. And on Tuesday, we will have a question answering session and quick revision. I hope that you will, inshallah, study hard for the final exam and wish you great success in the course and also in the other courses, inshallah, in this semester. Talk to you on Tuesday. Assalamu alaikum wa rahmatullahi wa barakatuh.